Welcome to the course Representations of Finite Groups. This is lecture number 18. Today we are going to define induced representations. Now recall from lecture number 17 that if H is a subgroup of the group G, then we have a linear map which we denoted by induction from center of group algebra of the subgroup H to center of group algebra of the group G. So this induction map take a class preserving function on the subgroup H and map it to a class preserving function on the group G. In particular, if we take character of some representation of the subgroup H, it's a class preserving function. So under the induction, it will go to a class preserving function on the group G. Today we are going to show that class preserving function on the group G is in fact character of a representation on the group G, and that representation comes from the representation of the subgroup H. That will be called the induced representation. So let's define it. Let G be a group and H a subgroup of the group G. All our groups are finite here, and let us say M be the index of the subgroup H in the group G. Let us fix a set of left coset representatives of H in G. So let T1, T2, so on Tm be a complete list of left coset representatives of the subgroup H in the group G. Now suppose that we are given a representation of the subgroup H and we want to define its induction, which is a representation of the group G. So let phi from H to GLDC be a representation of the subgroup H. We want to define induction of phi from the subgroup H to the subgroup G, which is a representation of the group G, which is a representation of the group G. Let us set a notation here which is analogous to induction of a class preserving function from the subgroup H to a class preserving function on the group G. Define this dot notation phi dot of x as follows. This is simply phi x if the element x is in the subgroup H, and 0 if x is not in H. Note here that phi sub x is a d by d matrix where phi x is in GLDC by definition, because phi is a representation of the subgroup H, and as you understand 0 is a d by d 0 matrix and 0 is a d cross d 0 matrix. Once we have this, define induction of the representation phi from the subgroup H to the group G as a map from the group G to GL of MDC, the group of all MD cross MD invertible matrices over C, where M is the index of H in the group G and D is the rank or the degree of the given representation phi of the subgroup H. So define induction of phi from H to G as follows. If little g is a group element, then induction of phi from H to G on a group element and define its ijth block, which is a d by d block, as follows. Set it as phi dot of Ti inverse G Tj for I and j bigger than equal to 1, less than equal to m. Then one can check that induction of phi from H to G acting on this group element G is in fact an element of GL M D C. So this check I am going to leave that this definition gives you an invertible matrix. So let's write the complete matrix. So what is induction of phi from the subgroup H to the group G acting on the group element G? It is this matrix, phi dot T1 inverse GT1, phi dot T1 inverse GT2, and so on, phi dot T1 inverse GTM, where phi dot at an element of the group G is just phi of that element if the element is in the subgroup and 0 otherwise. And similarly, second row, let me write second row for clarity, phi dot of T2 inverse GT1, phi dot of T2 inverse GT2, and so on, phi dot of T2 inverse GTM, and so on, phi dot of Tm inverse GT1, phi dot of Tm inverse GT2, and so on, phi dot of Tm inverse GTM. This is how the matrix of the induced representation at a group element will look like. So let's check whether this is actually a representation and find its character. Theorem: let H be a subgroup of G of index m, and let T1, T2, and so on Tm be a complete list of left coset representatives of the subgroup H in the group G. And let us take a representation phi of the subgroup H, phi from H to GL DC of degree D. Then this map, induction of phi from the subgroup H to the subgroup G, which I define it as a map from the group G to GL of MDC, is a representation of the group G, is a representation of the group G. Further, character of induction of phi from the subgroup H to the subgroup G is, as you can guess, it is induction of the character of phi from the subgroup H to the subgroup G. So let's prove it. For simplicity of notation, let us set this induction of phi from the subgroup H to the subgroup G as phi cap. Okay, just for the proof. To show that phi hat is a representation, we have to show it's a homomorphism. So take two group elements. So let X and Y be two group elements. Then consider phi cap at X into phi cap at Y. Phi cap at X and phi cap at Y both are MD cross MD invertible matrices over C. To show how it is related to phi cap of XY, I need to compare their ijth blocks. So consider the ijth block of this, and as you know how to multiply block matrices, it turns out it is just same as summation phi cap at X is ikth entry and phi cap at Y is kjth entry, where k run from 1 to the number of blocks, which is m, which is also the index of the subgroup H in the group G. So this is just same as summation k from 1 to m. And what is phi cap at x at ij? This by definition is same as phi dot of Ti inverse x tk and phi dot of Tk inverse y tj. Now recall the definition of this dot of this representation. So by definition, phi dot at a group element is phi of that group element if the element is in the subgroup and 0 otherwise. So for this product to survive, both the entries should be non-zero. So let us analyze what those entries are. Note that phi dot of Tk inverse y tj is non-zero, is not the 0 d by d matrix if and only if this element is in the subgroup. Tk inverse y tj is in the subgroup H. But this happens if and only if y tj of H is same as Tk of H. But y tj of H will be TL of H for some other L. So if TL is the coset representative of y tj of H, then we get phi cap x, phi cap y of ij. This is just same as summation k from 1 to m and phi dot of Ti inverse x TL. Why it is so? Because Tk of H is same as y tj of H, but y tj of H will be some TL of H, okay, because T1 to Tm are fixed complete set of coset representatives. So therefore I can take k to be L, and then the other dot I can replace by just phi of the value. So other one is same as phi of TL inverse y tj. Let's now look at the first factor here, phi dot of Ti inverse xtl. When is this non-zero? Again apply the same argument. Similarly, phi dot of Ti inverse xtl is non-zero if and only if Ti inverse xtl is in H, which happens if and only if TIH is same as xTLH. But what is TL into H? TL into H is same as YTJ into H. So that is same as XYTJ into H. And which happens if and only if Ti inverse XY Tj is in H. Therefore, phi cap x, phi cap y, and is ijth block, which is same as phi dot of Ti inverse xy Tj. And what is this? This by definition is same as phi cap of xy and its ijth entry. So therefore the ijth block of phi cap x into phi cap y is same as the ijth block of phi cap of xy for all ij bigger than or equal to 1, for all I and j bigger than or equal to 1, less than or equal to m. This implies that phi cap x into phi cap y is same as phi cap of xy. That is, phi cap is a representation of the group G. A very beautiful construction. Now let us find out the character of this representation. Let us now find the character of phi cap. Consider the character of phi cap at a group element. This by definition is trace of phi cap of G, but phi cap of G is a m by n block matrix where each block is a d by d invertible matrix. So the trace is just sum of the traces of the block matrices. So this is just same as summation I from 1 to m and trace of the block matrices, but that is just same as trace of phi dot of Ti inverse G Ti. But what is that? That is just same as summation I from 1 to m. Trace of phi dot by definition is same as trace of phi of Ti inverse G Ti and then dot of that. But trace of phi of Ti inverse G Ti is just the character of phi evaluated at that point and then dot of that. So this is just same as chi of phi acting on Ti inverse G Ti and then dot of this. But now recall a result from lecture number 17, that if you have a class preserving function on a subgroup H and you define the induction of that, so the induction of a class preserving function can be written as sum of the dots of that function, okay, as you run over the coset representatives. So therefore this is just same as induction of chi of phi from the subgroup H to the subgroup G. This by a result from lecture number 17. Character of induction of representation phi from the subgroup H to the subgroup G is just same as you take induction of the character of the original representation from the subgroup H to the subgroup G. So this proves the theorem. Let us now discuss some examples of induced representations. Let G be any group and take H to be the trivial subgroup. Let G be any group and take H to be the trivial subgroup. Then what are all representations or characters of the subgroup H? It is just one, that is the trivial. 1 goes to 1, the complex number 1. So let chi from H to C star be the trivial, which is the only character or the only representation of H, be the trivial character of the subgroup H. We now want to define what is induced representation. So let us first find the induced character of this character chi. So by definition, what is the induced character of this chi from the subgroup H to the subgroup G? So at a group element, how does it act? Which is the same as 1 by order of the subgroup H, summation x in the group G, chi dot of x inverse Gx. But what is this? This is just same as summation x in the group G, chi dot of x inverse Gx. Now chi dot of x inverse Gx is chi of x inverse Gx. If x inverse Gx is in the subgroup H, equivalently x inverse Gx is the identity element, equivalently G is the identity element. So if G is the identity element, this value is chi dot of 1, which is just 1 added group many times. So this is order of the group G and 0 otherwise. Which representation of a group has this kind of character? You may recall that a regular representation of a group has character precisely induction of chi from H to G. Recall that if phi is the left regular representation of the group G, then character of phi at a group element is exactly this. This is order of the group G if the element is trivial and 0 otherwise. Thus induction of chi from the trivial subgroup H to the group G is the character of the regular representation of G. But by the preceding theorem, the trivial character chi will induce a representation, okay, that we call the induction of chi, and the induced representation will have character as character of the induced representation. So by previous theorem, by preceding theorem, the induced representation of chi will have induction of chi from S to G as its character, but the regular representation also has induction of chi from G to H as its character, and two representations have the same character if and only if they are equivalent. Since representations having the same character are equivalent, it follows that induction of chi as a representation is precisely the regular representation of the group G. Thus, the conclusion is the regular representation of any group is nothing but the induced representation of the trivial representation of its trivial subgroup. Let's see another example. Now let H be an arbitrary subgroup of a group G, and let sigma from G to the symmetric group on the set of left cosets of H and G, G by H, be the usual action of G on G mod H given by sigma G acting on XH is just GXH, this coset. We have studied this action in detail when we studied permutation representations, so you can watch that lecture. Recall that a coset XH is fixed by G belonging to G if and only if, by definition, XH is same as G of XH, which happens if and only if X inverse GX is in H. So X inverse GX is in H, it could be any element of the subgroup H. Thus, the number of fixed points of the element G is same as 1 by cardinality of the subgroup H into cardinality of this set, that is all those X in the group G for which X inverse GX is in the subgroup H. Now let us repeat the same process as we did in example number 1. Take a trivial character on the subgroup H. So let chi from H to C star be the trivial character, that is chi of any little h is just the complex number 1. Then we note that what is chi dot of X inverse Gx? By definition, it is chi of X inverse Gx if X inverse Gx is in the subgroup H and 0 otherwise, and chi is trivial character, so it is 1 if X inverse Gx is in the subgroup H and 0 otherwise if X inverse Gx is not in the subgroup H. This implies that the number of fixed points of G, the number of fixed points of this group element G, which is same as 1 by H times the cardinality of the set of all those X in G for which X inverse Gx is in H. So which is same as 1 by cardinality of H and cardinality of this set written over here. But it is the collection of all those elements of the group G for which X inverse Gx is in H, and for all such element X dot count 1. Okay. So this is just same as summation all those X in the group G and then chi dot of X inverse Gx. And now recall this formula. This formula is 1 by order of the subgroup H, summation x in G and chi dot of x inverse Gx, which by definition of this dot construction, this is induction of the character chi from the subgroup H to the subgroup G acting at a group element G. On the other hand, we have the action sigma from G to symmetric group on this set of coset G mod H, and look at the corresponding permutation representation. So, there is an induced permutation representation which we denote by sigma tilde of the group G. Every action of a group on a set gives rise to an action called the permutation representation corresponding to that action. And you may recall we denote such a representation by sigma tilde. Recall that character of such a permutation representation sigma tilde acting on a group element G is precisely the number of fixed points of G. Number of fixed points of G under the given action equals to the number of fixed points of G, which we have just shown above here in star is same as induction of chi from the subgroup H to the subgroup G acting at a group element G. So, what does it show? It shows that if you take a subgroup H of a group G and take the trivial character of the subgroup, then the induced character is precisely character of the permutation representation of the coset action. And we know that two representations have the same character if and only if the representations are equivalent. Therefore, the representation induced by a trivial character of the subgroup H is precisely the permutation representation of the coset action. Thus, the induced representation of chi is the permutation representation sigma tilde of the group G, where sigma from G to S of G mod H is the coset action. If we take H to be the trivial subgroup, then we recover example number 1. So, in that sense, example 2 is a generalization of example 1. Let us see some more example, some concrete example. So, dihedral group and quaternion group. Example number 3, let D2n be the dihedral group of order 2n, which is generated by two elements R and S, where R to the power n is 1, which is same as S square, and S R S is R inverse. So, let us take H to be the subgroup generated by R. Then index of H in D2n is precisely 2, and 1 comma S is a complete list of coset representatives, is a complete list of coset representatives of H in the group D2n. Notice that in a general situation, if you have a group G and a subgroup H, and when you take the cosets T1 to Tm, without loss of generality, you can always assume T1 is the identity of the group, because there is always a trivial coset. So, you can always take T1 to be 1. Consider the representations chi superscript k from the subgroup H to C star given by, we know H is a cyclic subgroup of order R, and we know what are all its inequivalent irreducible representations. So, given by chi k of any R to the power m, you can just set it as e to power 2 pi I k m by n. We have already discussed representations of abelian groups in detail in previous lectures, and they all are distinct at functions, so they are all inequivalent, and of course they are irreducible being one dimensional. We want to understand induced representations of this chi k's from the subgroup H to the group dihedral group D2n. Setting T1 equals to 1 and T2 equals to S, we can compute the elements Ti inverse G Tj for all G in the dihedral group D2n, right? And recall that D2n as a set, you understand it very well. This is just 1 R, R square, so on, R to the power n minus 1, and then there is S, SR, so on, S R to the power n minus 1. Exactly this set. By hand you can compute it, and then we see that induction of the subgroup H on to the group D2n of chi k at the group element R to the of the form R to the power m. You can check and find that this is by definition. So what has to be the degree of this representation? Degree of this representation has to be degree of the original representation times the index, and index of H in D2n is 2, so it is degree 2 representation. So you should get a 2 by 2 block matrix where each block is of size 1, which is the degree of the original representation. And you see that this is precisely chi k dot of R to the power m, chi k dot of S R to the power minus m, chi k dot of S R to the power m and chi k dot of R to the power minus m is precisely same as this matrix, e to power 2 pi I k m by n 0 0 e to power minus 2 pi I k m by n. And what about the other kind of elements? Induction of chi to the power k from the subgroup H to D2n on elements of the form S R to the power m. You can similarly check, and you will find that you can write it as 0 e to power minus 2 pi I k m by n e to power 2 pi I k m by n and 0. If you have seen the lecture on representations of dihedral groups, you will see that representations of dihedral group, whatever the parity of n may be, even or odd, they are like this. A direct check shows that these induced representation induction of chi k's from the subgroup H to the full group D2n is irreducible for all k bigger than or equal to 1 and strictly less than n by 2. Notice that induction of chi k from H to this subgroup D2n is just same as induction of chi of n minus k, okay, from the subgroup H to the group D2n. So therefore you can forget about the remaining half, and then the precise value you can find depending on the parity of n. And also we know that if n is odd, then the commutator subgroup is precisely subgroup generated by R square, and therefore the number of degree 1 representations is precisely 2, and if n is even, the number of degree 1 representations is 4. So that way you can get all inequivalent irreducible representations of the dihedral group as discussed in one of the lectures. What I am trying to say in this example is that you can obtain a complete list of inequivalent irreducible representations of the dihedral group by induction of representations of its subgroup generated by R. Let's see one more example, last example, the quaternion groups. So let Q be the quaternion group, Q8 be the quaternion group of order 8, which has plus or minus 1, plus or minus these symbols I, plus or minus symbols j, plus or minus k, with there are this multiplication rules with I square equals to j square equals to k square equals to I j k is equals to minus 1. Let us take H to be the subgroup generated by this I. then H is in fact the cyclic subgroup of order 4 and has index 2 in Q8. Then order of H is 4 and H has index 2 in the quaternion group Q8. So you can choose set of coset representatives. So let 1 comma j be a set of coset representatives. You could have also chosen 1 comma k. Let 1 comma j be a set of coset representatives of H in the group Q8. Let phi from H to C star be the representation of the subgroup H given by phi of I to the power k to be I to the power k. So notice here that I am using the notation I, j, k as elements of the subgroup H, where I is also the complex number iota. Okay, so because you can always embed complex numbers inside quaternions. Okay, so I don't want to bring more notations. So if you like, you can just change I, j, k as I hat, j hat, k hat, and in that case you can map phi of I hat to the power k as I to the power k, where I is a complex number. Then we compute induction of this phi from the subgroup H to the quaternion group Q8, and you can tell me how does it act on the elements. So on plus or minus 1 it acts as, so by the way, what is going to be the degree of the induction here? Degree of the induction is going to be degree of the representation H times the index. So degree of the representation phi is 1 and induction, and the index of H in Q8 is 2, so it's going to be degree 2 representation, and it is given like 1 0 0 1. You can write induction of phi from H to Q8 acting on plus or minus iota as plus or minus iota 0 0 minus iota, and similarly induction of phi from H to Q8 acting on plus or minus j as plus or minus of 0 minus 1 1 0. Finally induction of phi from H to Q8 acting on plus or minus of k, and that is plus or minus of 0 minus iota 0. Just write down the definition and you will see that you can compute the induction like this. Is this induced representation, induction of phi from H to Q8, is it irreducible? You can easily check that it is irreducible because it is a degree 2 representation, and either you can compute the character of induction of phi from H to Q8, or you can use the fact that degree 2 representation is irreducible if and only if all the elements of the group G do not have a common eigenvector. Since induction of phi from H to Q8 at I and induction of phi from H to Q8 at J do not have a common eigenvector, do not have a common eigenvector, it follows that induction of phi from the subgroup H to Q8 is irreducible. So we have seen plenty of examples to illustrate how induction really works. Now here is a natural question. If you have a subgroup H of a group G and an irreducible representation of the subgroup, what are the conditions under which the induced representation is irreducible? As we see from the example that we just discussed, induced representation of an irreducible representation need not be irreducible. For example, when we take the trivial representation of the trivial subgroup, we got the regular representation, and we know that regular representation is not irreducible. So in general, induction of an irreducible representation is far from being irreducible, but there are conditions under which induction of an irreducible representation is irreducible, and these conditions are due to Mackey, and so we will find a criteria for induction of an irreducible representation of a subgroup to be irreducible. So we will do that in the next lecture. I will stop here. Thank you.